Okay, so then let's start. Thank you everyone for joining today. We have a session on JuliaStats. Let me already share my screen. You see in the chat the link for today. I hope also the new ones can see it. You should be able to. So it's my binder.org link, which points right to this very notebook, which I have active also here. So if you press the link, you should get a very similar setup like you see here on my shared screen. So then let's keep this active. Let's start. So you are joining Julia User Group Munich today on a Fallen Law in Julia introduction session. And this time I picked out the statistics ecosystem. And yeah, so this is a really big thing here, and we are going to look at a couple of small bits here and there. So the ecosystem itself is called JuliaStats, and one of the meta packages which I take as the red thread is the StatsKit package. To start, some words about me. So I'm Stephan Sahm. I'm organizing this meetup since like 2 years, I think now, quite some time by now. And and we've organized a lot of these sessions, a couple of recordings you can find online. And since recently, I've also launched my own Julia consultancy. So if it's called Julien, you've also find it here in the icon and the banner. If you have some request, want to spread Julia at your place, academia or company, everything is welcome. I'm very happy if you can reach out to me and we can see what we can make. Okay, so let's jump into it. This binder setup, as usual, is a Jupyter notebook, and it might turn down because you haven't used it for 15 minutes or something. So this is normal because it's free resources, and I'm always proceeding from cell to cell by using Shift-Enter, but you also have this Run button here at the top where you can use execute a cell. But Shift-Enter works really nicely and brings you to the next cell. Okay, so what is StatsKit? Let's jump into it. StatsKit is actually almost nothing on its own. It's just a meta package which combines a couple of standard statistical tools. So that you just have to import one single package using StatsKit and you have everything available. So for this session, this is just a guideline so that we look at a couple of packages which are loaded in here. And for your daily work, it may make sense that you really make using StatsKits as your first call and just experiment a bit. But as it loads really a lot of packages, which you may not need to kind of make things a bit faster in loading time, actually then finally you may want to import these packages on their own. And this is also what I'm going to follow so that you also see a little bit the dependencies so that we take a look at a couple of these things step by step from the most built-in to the base and so forth. Okay, that's the start. I want to show you the missing type. So a couple of you definitely already know, but this is one of the crucial differences to Python and to the R ecosystem, that you have a special data type called missing, with which you can indicate that some data point is not there as expected. And this is really important to note, because in the other systems you have not a number type, which is usually the missing value, but not a number also comes up if you have some floating computations which behave illy, and this is quite a problem, that dynamically you can get kind of a none. This is interpreted as missing, and it's not a nice setup. And in Julia, this is solved from the ground up, and it behaves very similar to none itself. So if you compare missing to missing, I'm not sure whether you're familiar with floating point operations, not a number behaves very similarly. So you cannot compare it. Yeah, it just returns again another missing. It's just like a blank state. So this is kind of the basic behavior of missing. And if you call some statistical operator on it, yeah, I'm importing the first package. We'll look into it in a couple of seconds. It's also returning missing. And the way to handle missing is then to really do it explicitly. Yeah. And in this case, the standard function is skip missing. So this just takes a vector or iterator and returns something which does not have the iterator, the missing in there. So this really works and does the correct mean. And to see kind of that this is not a special function which is doing some special logic for skip missing, you can see the method which is called here. It's really the standard mean, and it's a bit cryptic, but it's ITR. So iterator. So this is really the standard method which is called here, and the magic happens in skip missing itself. So you can also use the standard collect to get an iterator to an array, to a vector, and you see that the missing is gone. Okay, so this is very basic data type, but also very helpful. And one of the advantages of our Python and R, I would say. If you have questions, meanwhile, or kind of after such a block, you can always, thanks. You always give hints in the chat or ask questions in the chat. I'm monitoring the chat and can react. Thank you for the mentioning of the NA value in R. I have to look this up. So, would be curious to know whether this is very similar to the missing type. I think not, but I would be interesting to know whether there's some approach similar in R. The second, that's used, so we have some, so it's definitely used in that way, but it has some edge cases which are happening here and there, which is not that optimal. But so I want to then go, as I always ask questions in the meantime. Next little tool is categorical arrays. So you can simply construct arrays in Julia by using the square brackets, and then you get an array. But if you work with categories, which is like very common if you do some statistics here and there, then you also want to somehow preserve the levels, and the categorical array is for this. So it wraps all elements within a little category wrapper. We can inspect this. So in Julia, unlike others, you start with 1. Unlike Python or R language, the first is the index 1. And as you see, it won't return a string, but it returns a categorical value. And and this is kind of the special support here. You can access the original value by calling the unwrap function, and you can also write new stuff onto it. And you see it just works, but you can wrap it into a categorical value. And now comes the most important thing. This also then stores the levels, and you have it on the array, and you also have it on every single categorical value, so that whatever you use, you remember from which category it was. So that's a very handy little function. And I hear some noise. I will look into who's kind of not having muted themselves. But here's now the first little exercise. So those of you who have this notebook ready, this binder notebook, Jupyter notebook, I would like you to experiment with this categorical array and just adapt this line so that you assign some new value and take a look what happens. Okay, so mute seems to be gone. The noise seems to be gone. Jan, I see that you have muted yourself. I will mute you now. Okay, so it was a very, very simple exercise, and I definitely want to show also those of you who are maybe not doing it hands-on. So if I do some new stuff here, yeah, which was not there, it works. So yeah, you may have expected that it throws an error or something, but no, this is quite flexible, so it works. And yeah, you get the very same result. And it now included itself to the levels. So that's quite interesting stuff. And you also have it kind of on all the other elements. Yeah. So okay, this was not in our vector. So this is nice utility. So you can really flexibly work with these categories and be sure that the category itself, the levels, are always updated correctly. Okay, so then I want to go to the next package, or the first package in this sense. And yeah, and this is statistics. This is the built-in package from Julia, which is now having only a couple of functions. So from now on, so we have kind of, I would say, the biggest part in the middle, where I'm showing you more or less only functions, so that you know, okay, this is there, I can use that. And yeah, so I prepared kind of these overview tables that you have a good idea what is the provided functionality. But yeah, compared to the data types which we just saw, so the missing and the categorical array, we are now looking at functions. Okay, so yeah, statistics comes with really the core stuff. So we have variance, standard deviation, mean, median, the middle point, a little bug, correlation, and covariance, of course. So this should be V. Okay, so you can take a look at the functions. So as always, you can use the question mark in Julia to request the documentation, and you get a lot of helpful stuff on it. So you can also search it online, of course, but it's also available in every Julia interpreter. So you would have it here, and same goes for the others. And yeah, and this just nice to know. So just some Julia regularity. So you can use UTF-8, and the square root you can get by having a backslash and SQRT, and then you have to press tab, and you get the square root. And you can also copy and paste it because it's just a normal character. It's UTF-8. Okay, so we can apply take the mean of something after applying a function to each element. So this is really the same. We can also do it in a matrix session and yeah, have it multidimensional. So here we have for every row we computed the mean. So this is the result. And yeah, what I also want to show you here, so it's really you know the functions probably by heart. I just wanted to go into the covariance and correlation because they don't have an example in the standard documentation. So I'm plotting here some very, very similar series. So you see I've kind of 1 to 10, the diagonal, and then I'm adding some random stuff here and plotting it. So you see it's really very, very similar. And this is kind of the basis for some correlations or some meaningful correlation values. And I also put here, that's just the definition. So the covariance, like a normalized difference from the mean, or yeah, co-difference from the mean. But it's not really normalized, but the kind of true normalized version is the correlation. So this is then from -1 to 1. And yeah, you can see it also that it's really the very same numbers. If we used this normalization on our own, we get the very same. So the correlation is the same as the covariance normalized. And yeah, so just to point out, this correlation is really interpreted like these differences from the mean. So the absolute value doesn't matter so much. So this is a correlation of 1, good to keep in mind. And here another matrix example where now the columns are compared against to each other. So this is the interpretation if you just, so this is here for 2 arguments, they get compared directly. And if you just have a matrix, it's compared every column against every other column. So hence the diagonal is 1, so it's like the correlation matrix. Same for the covariance. Yeah, and you can get a feeling, yeah, if you inspect these numbers. Just if you like, so this random factor is really to make it a little bit more interactive. So if you add some randomness, we should get smaller correlations. And this actually is also the case. Yeah. So if we make it super random, then yeah, we should approach a correlation of 0 in average. Okay. So that was the first package built in. So with every Julia, statistics ships with it. And the next layer on top of this is StatsBase. And yeah, and this kind of provides a fuller set of standard tools, standard functionalities. And as you will see, it also integrates well with the built-in, so that there's no clash, but everything is reused what can be reused. So again, the little tables, there's much more in here now, as you will see. So we have geometric mean, harmonic mean, a generalized mean where you can say to which power you want to take it, skewness, kurtosis, moments, variation, the standard error of the mean, the median absolute deviation. I especially like this one. So using the mean is, as you know, kind of a little bit unstable, as one single big or small, super big or super small value, yeah, corrupts everything. And yeah, and hence you probably know about the median. We've seen it. Yeah, so this is one of the standards which you can use alternatively to the mean to make things more stable. And everyone knows that, but that there's an alternative to the variance also. This is kind of something which not everyone knows. So, and this is the one, the median absolute deviation, the MAD. This is the stable alternative to the variance. So very, very important and simple statistics. Robust. Thank you, Helmut, for sharing some infos. Okay, I will leave this to the reader. Sounds like a little side exercise. Thanks. Okay, so what we have else is Z-score, percentile, the interquantile range. Also a nice helper method nQuantile, so that you don't have to think about which percentages I need. If you want to have three equal quantiles, 3 equal intervals of your range, you can use an nQuantile with n3. And yeah, same with others. Sometimes this is easier, and yeah, only needs one input parameter, quite handy. You have also the modes, so the maximum values. Thanks, Benno. Yeah, the robust statistics. So median and MAD are the most typical robust statistics you can use. Then there are a couple of further stuff. So in multi-dimensions, we have a partial correlation, a generalized variance. So on the total variance, 2 different ways to how to generalize the variance. One's with the determinant and the other with the sum of the diagonal. And because it's quite nice to illustrate. I put here this little demonstration of the partial correlation. So yeah, to get this point, you have two vectors, or yeah, this is kind of 3D, but this could be in principle, yeah, ND, very many dimensions. And you have in the partial correlation one extra vector, which is kind of the dependency between the two. And this is here called Z. In the standard correlation kind of corresponds to the angle between this original Y and this original X. So this would be kind of a larger angle. And the partial correlation now takes the tangent plane. So it takes kind of the projects everything on this orthogonal plane to the help the dependency vector. So you see that X is projected here on this plane and Y is projected here. So this can also be a hyperplane, of course. And then the angle between these projected arrows is used. So this is the partial correlation. I find this visualization very, very useful. And yeah, in case you have some dependency like this, so yeah, keep this in mind. This is called partial correlation. Okay, so then there's some counting stuff. So you can get counts, proportions in different manners. There's also a cumulative distribution function. We're going to see this later. Histograms, some level handy, yeah, some helpers for levels. And yeah, and also one hot encoding here. So quite a mixture of things if you want to count stuff. For probabilities, there's entropy, the I hope I can pronounce it correctly, the Régnier entropy, the cross entropy, KL divergence. So very basic set of probability related statistics. And for time series, there's also the very basic, the autocorrelation and autocovariance, and yeah, cross correlation and cross covariance. So to explain this, I copied here from Wikipedia. So the cross correlation is a measure of similarity of two series as a function of the displacement of one relative to the other. So if you have a time series, you compare it kind of to what happened in the past. And usually there's quite a large correlation between the near past and only a small correlation to further away events. But if you have kind of periodicity, then of course the similarity, the correlation is again huge if you get the right legs, so-called. And yeah, and if you have this cross setting, you can think of this as a sliding dot product or a sliding inner product. So it really searches, it's commonly used for searching a long signal for a shorter noun feature. I pretty much like this description so that you get an idea. So yeah, this is really, the autocorrelation is really just a cross correlation which is with itself, same for autocovariance. And yeah, and you can kind of also use this to find time series patterns in another one. And there's a very helpful fifth function, the partial autocorrelation function. And yeah, and this is a little bit more stable. So, or yeah, a little bit smarter. It already cleaned up everything so that if you have a lag at one time step back, which is really, really very pronounced, where there's a strong autocorrelation, this will typically also be the same for the lag 2, so getting time steps back into the past. And the partial one will now compute kind of everything from the first part already out, so that the second leg really sees only the stuff which is new. So that you don't have, you will see the right legs or the right time step differences in this partial autocorrelation function. If you use ARIMA models or the like, then this is the one you want to use to estimate your lag parameters, so your time steps, which you want to have a linear dependency to the past. Okay, this was now a little bit detailed, or yeah, not super simple explained, but I hope you can enjoy these little extras here and there. Okay, so StatsBase comes with a couple of more stuff. So they have also another section on robust statistics, where they can trim certain data using also the Windsor approach. So just take a look at them. But yeah, the median and the MAD are also robust statistics, which don't turn up in this section. We have the deviations also between two arrays. We'll look into another packages called distances later, but there are also already some common distances in here. So if you want to just compare two representations, two vectors. There's also the ranking. This is kind of more standard statistic now. You have a lot of ranking functions. And there's also a function sampling, which we use later on. Okay, so let's just look into some little things. So here I want to show you that statistics is really building upon the built-in statistics. So with this rich macro, I look where it is really defined, and you see that the StatsBase standard deviation is indeed coming from statistics. It's adding a couple of more functionality here. I skimmed over this in the overview. I made a little note here on the top. I haven't read it out loud. But in case you want to have weights on your data, so that certain data points are weighted differently, this is supported and supported everywhere. So it's a nice feature. You can look it up on the StatsBase. It's really the first thing which comes up. And yeah, integrated also with the standard function. That's why I remembered it now. So even if this standard deviation lives in statistics, so this is the interface, it was now provided with some further features, namely also the weights support. Okay, so there's another nice function handy kind of for quick introspection. There's a summary stats function I haven't named above, which gets, yeah, the classics and also the missing count. Very interesting. Okay, so then I want to show you that there's a histogram support in this package. Usually you won't need this. So this is kind of a, yeah, always done on the plotting side. But in case you do the statistics and really want to work with histograms, take a look here. So the way you use it is with the fit function. We will see it later on again. And yeah, you have a histogram and you fit it to some observations and bins. And this is just a special example where we have continuous numbers and we can take this into account. And here they use the interface from the linear algebra. It's also one of the built-in packages and the normalize function. And if you call this, then we get other weights. So in the first part, we have the counts, which are in this field. So here we have kind of one large bin, yeah, between 1 and 7, where there are actually 3 observations, and one small bin between 0 and 1, where there is only 1 observation. And not normalized, we just have the counts 1 and 3, and normalized we take into account also the length of this interval. So yeah, that it's really indeed the other side around. And yeah, you can also merge these histograms. There's a little bit more support on these. So it's really intended for programmatic use. So if you want to just plot it, that's not the way to go. You can just use the histogram function. We will see it later to plot it. And just for completeness, there are also some standard transforms in the StatsBase package where you can transform your data. Yeah, some call it whitening. So here's a Z-score transform or a unit range transform. So this was the StatsBase function. And yeah, I'm very happy to explain a bit more, just raise your questions. Yeah. Okay, I just read your comment, Helmut, quite some time back in full. Yeah, so the missing feature is very well supported. Nice. I have to take a look how this actually is done internally. Okay, so next package, and it's still in this flavor of very basic packages. So just the toolset which you would like to have in a language built for data science and statistics. So this is called distributions. It's also, as the others, part of the StatsKit meta package, but it's very well known and widespread on its own. So it integrates again very well. So we have functions in it which come from statistics and to get extra support here. And we have also some functions which come from StatsBase and which get extra support. So this builds upon the other two which we've seen. So the way this works here is that in this distributions package, as the name suggests, you get kind of all standard distributions you would like to have. And to illustrate what you can do with them, I just use the normal distribution. So we can always construct a distribution using this distribution name. There are a couple of more. We can take a look also if we get the distributions package and make a dot in, then we can also have the completion. And you see then by what names are actually here, all the different distributions themselves. But it's a little bit easier to go to their web page and look through the nice documentation. You can find all the different distributions divided by univariate, multivariate, and there's another distinction I just forgot. So it's always nice to see your distribution. So this would be one way to plot it. Plot standard function supports to get a function itself. So, and the standard range is from -5 to 5, something like this. And we plot the probability density function. So we take our distribution and then our value itself, and this is then thankfully plotted nicely by the plots package. There's also support for certain fields. So every distribution type has their own fields, and the normal distribution is just characterized by the mean and the sigma, the standard deviation, and we can also grab them by the standard functions for the mean and the standard deviation. So usually this kind of syntax is an implementation detail, but in this very special case, it's just so handy that this is part of the standard interface. So you're invited to also use this dot axis like you're familiar. But in general, like if you build your own things, it's always good to think about having these axes of functions. Oh, sorry. Okay, so another function which works is the random number generator. So here we get our distribution and can now sample from our Gaussian, from our normal distribution. And this is the function I named previously, the histogram function, which comes from plots. So here we can now have another representation of our Gaussian distribution by this 1,000 samples. And if you just want to see a histogram, this is the way to go. Yeah, so this is much simpler, and then you don't have to mess with the data. Okay, so we can also apply mean and standard deviation to this, of course. And then there's a nice two different functions to actually work with these distributions. The one is truncated, where you provide a lower bound and an upper bound and get a distribution which then renormalized, assuming that all the probability mass is within this range. And we can also plot this. I now need to specify kind of the x and get the function as the y. And yeah, so to make it a bit larger, otherwise you would have just from -5 to 5. And in this example, I took larger values. So you see, that's just a discrete jump here, yeah, that after -10, the probability mass is down to 0. And same for higher than 20 values. So this is quite handy. So you can take whatever distribution you want and yeah, and make it kind of one-sided for an example, yeah, and make sure that it's really one-sided. And the nice stuff is that this still works, yeah. So all the functionality is still there. Then, as a very similar approach, you have the Sensort method, and it's again good to see the plot to understand a bit what's happening instead. So you see the plot is a bit different. So the one, I now have to scroll back and forth, but maybe you can see it on your side easier. So here we have the peak a little bit higher than 0.04, and here it's a bit on 0.04. So it's really not the same peak. It's a little bit lower, and instead we have probability mass here on the -10. It's we can easily see it by this discrete jump, but in fact it's just the -10 which gets the probability mass, and here for 20 it's the very same. So what happens is that what the whole probability mass which comes after the boundary, so here the upper bound, gets put onto the bound itself, and the same here on the lower bound. So this is also the reason why we get kind of two different heights, because the 20 is a bit further away from the mode, from the peak. So there's less probability mass to be summed up. Okay, last very handful utility for every such distribution is the fit function again. You can just get some data. Here we take the data which we sampled ourselves and fit a normal to it. So here it also makes much more sense to really use an additional function. And so we don't use the normal constructor because it just takes other input variables, and we instead use this well-defined fit semantics. And this works with all the others as well. And finally, I also want to show you that there's support for mixture models. So you can plug together or add together a couple of probability distributions and give them weights. So the second vector is the weights, and we can also plot this and see some fancy Gaussian mixture. There's a special package also for this. I haven't put the link in here. It's called Gaussian Mixtures.jl, which gives you a little bit more features if you really want to work with Gaussian mixtures. They're very powerful model. You can estimate a lot of distributions by using Gaussian mixtures, and they are also analytically traceable. So they give, they are just a nice interface and a nice framework. Okay, so I have written here another little exercise. If you're hands-on, feel invited to also do it on your own. I will do this little exercise now also live. So task is construct a distribution with two equally probable peaks and get the 80% percentile or .8 quantile. Okay, so should be kind of straightforward. You've seen kind of the syntax in between that we can provide some arguments to the normal distribution, namely its mean and its standard deviation. And to have them equally probable, it's probably easiest to just have the same standard deviation, and different means, like put them neatly together. So now I want to get them into the mixture model. And to ensure that they are very same, I also make them having the same weights. Now let us plot this. This doesn't work. Okay, so we need to have a smaller variance, I guess. Or yeah, because the standard plot is from minus 4 or -5 to plus. I think it's easier if we put -3 and 3. So let's see. Okay, so this worked. Okay, so this just for illustration. And now I would also like to have the 0.8 quantile. And so 80% are left to somewhere here, just left to this point. So yeah, to make the check, maybe it's easier to see it at 50% because this should be 0. Yeah, and it's kind of 0. Yeah. Yeah, 10 to the power of -11. It's very much 0. Okay. Going forward, next package I want to show you is the distances package. It's similarly focused on one task. So yeah, from what we've seen up to now, I think the stats base package is a little bit messy. So there are a couple of things in there, and it may be indeed that others feel similarly, so that functionalities are taken out into their individual packages, but such moving is always takes a lot of effort. So yeah, not sure when this happens. And yeah, we have to live with stats base being a bit messy, I bet. But nice to see that there are kind of these really clear focused packages, and distances is one of them. And yeah, to my very surprise, I don't get a warning on my test today. I got a warning, and this is because I actually found one conflict between them, but turns out that the newest Julia version, I'm on Julia version 1.7.1 on my system, probably suppresses, down shows this warning until it happens. So there's not so nice conflict between functions, just that it's still kind of a set of packages. And here the mean, I forgot what it does. The mean absolute deviation between two arrays. Okay, so this is the same function defined in the one and the other package, and they don't reuse each other. So yeah, if you want to use mean at like this, you will get the warning that they both export the very same function. So you cannot accidentally use the wrong function. This is quite nice, and one of the big things where I like Julia compared to R, where you have a similar setting, but yeah, things get easily out of hand. But you see that the mean absolute deviation is not even defined here. We really need to use a qualified, as it's stated here, qualified access. So as we did it before with the stats base mean at, or the distances mean at. So good to know that Julia in general is safe on this side, so that if you have a conflict, it's safely handled. But still, here are two packages which compete about the ground truth. Yeah, so of course distances would like to be the ground truth about what a mean absolute distance is, absolute deviation is. Okay, that was a little side note. So how to use this distances package is a bit different. You have kind of also the I call a function. So you can you have also functions where you can compute Euclidean distances. So this works, but the standard functionality, or where it really shines also in performance, is when using this as a type. So we have here the Euclidean type, and this can then be used with a higher level function, and this part here column-wise. So we compute column-wise distances. And this is so typical when computing distances. You usually want to compute distances between a lot of things. To then put this distances matrix to your next step of a dimension reduction or similar. Yeah, and hence this part really, yes, this part really is one of the parts which you want to have optimized. I see some comments in the chat. Thank you for being active there. Yeah, thanks Helmut for pointing out you can also explicitly import a version. And in case this even doesn't work, you can even override it yourself. So just sometimes you, yeah, I won't, yeah. Okay, yeah, thanks for the additions. So this column-wise stuff now expects two matrices which have the very same number of columns. Yeah, so I have now here, and actually also the same number of rows because it compares them. So they need to be of the same shape. And it really compares the first column. So let's take a look what this random constructs. So this constructs a 10×3 matrix. And the column-wise distance now compares this matrix to another random matrix. Yeah. So the first vector to another random vector, then the second to another second, and the third to the other third. And we get these three distance values. And even more typical, you want to compute pairwise distances, and there's also special support for here. Now I'm using another distance, the Hamming distance. If you go to the page, it's very, very simple. They list all the distances they support also with mathematical formula and standard name. So this is easy to get which things are supported, but also you can of course also use the autocomplete here. So you see there are a lot of distance matrices, distance types, and there are also some further functions which are really nicely also using underscore and some further functions. So this is actually very concise. So you can use the autocompletion because it summarizes all capital stuff in front. So you see the distances in front. So yeah, luckily helpful. So now let me show you this pairwise part. So what we need here are matrices with the same number of rows, but can be different columns. So we again compare column-wise. So we take now every pair of columns. So we compare the first, the first column of the first matrix to the first column of the second, and also to the first column of the first to the second column of the second, and we get these distances then. And this is super optimized. So they make a little note on their page that they've spent really a lot of effort to get these in super fast. So you know, hopefully already that Julia itself is very fast. So you could write a simple for loop, which is already very efficient. But yeah, you can take into account a couple of extra information because these pairwise things, they also have kind of some internal structure. You can make it more efficient. I myself, I'm not the professional to do this, but yeah, they implemented it and they get kind of really a speed up of a factor of 10 over standard Julia. So they did even further immense improvements on this. So if you want to compute distances, this is super quick. And hence, I think the go-to packages. So yeah, just because of Julia is really bound also to performance requirements. So hence, I think this distances packages indeed, can demand of itself to give the standard definition of a mean absolute deviation. It makes a little bit sense to me. Okay. We are approaching the first hour. This was kind of my part on summarizing some functionalities. So you've seen kind of a couple of standard functions, and yeah, the feature set is very, very large. You have a couple of statistical functions here and there which you can just use. I bet that R might have some special statistics which is not yet in Julia, but feel invited to just open a pull request to the respective package I've shown you, so that this function will also be included in future versions of these packages. But it's already very rich in features and very rich in functionality. The next part is that I want to go into hypothesis tests. So actually, there are also a couple of functions, but then afterwards, I want to show you kind of how you can use what we've just seen to do some hypothesis tests on your own. So yeah, bare bones, but starting with not bare bones, but with functionality provided. So I'm using this hypothesis tests package now, and creating some random normalized variables. And the two main functions here provided is p-value, and which is the p-value. If you know about hypothesis tests, this is kind of the value which shows you whether your hypothesis test was successful, means a small p-value, or it failed, that means a large p-value. So there are a couple of tests provided here again, with the style of having a type for it. So we have one sample test, which we can apply to our data. And we can also specify the distribution of it, whether we only regard the right side of the distribution as decisive or both tails. I don't want to go into detail here. But for those who use it, you know that this can be important because it gives you a wider confidence interval, or you have a bit more flexibility on your p-value. Or still in other terms, this is decisive for how significant your p-value is. Okay, so what do we see here? Okay, the p-value is very large. So this is a p-value almost to 1. So probably our test failed. So what does this t-test do? It shows that the mean is actually different from 0. So this the tests always indicate to reject something, namely the null hypothesis. And in this case, we indeed use the normal distribution with mean 0. So we expect this test to fail. So we can also compare, you have a lot of other statistics. So as you see by the name, this is really specialized on statistical tests. And we can do this first one is kind of again this t-test again. So, but now we can also place the mean itself, so as a second argument to it, and we can put it to somewhere else, and we see that this test is indeed significant. So we get something super 0. And now it compares not to a 0 mean, but to a mean of 5. So this is the most standard test out there, the t-test. There's also another test, and here with me, I forgot its name. So an Anderson-Darling test. And and with this, you can compare the data with the distribution itself. So here we can use again kind of any distribution which you want, which is a very flexible test setting. And if you haven't known this, there are also other tests which have this flexibility, but the Anderson-Darling test is one of them. And it's good to know that you can make such simple tests. So I find this very easy to read and nicely. And you see, of course, bam, it's really, again, a large p-value. So large means near 1, because, of course, we sampled from a normal distribution. There's an alternative way. Next to this p-value, there is the confidence interval function. And it has kind of a similar setup. And now it takes, the default one is that it has kind of a coverage of 0.95%. So we have a confidence interval where 95% of the options are in. And compared to the p-value now, it means you don't want to be within this confidence interval. So if you're in here, you cannot see anything. And if you're out of this confidence interval, you can reject your null hypothesis. So your statistical test was successful. Yeah, so this is kind of a different interpretation of the very same. And it's also supported on all. It also has this tail. So if we make it just right, we see that there's a much, should be a, so the left, if you have both, then we cut our probability mass also to the right. So we need to spread it a bit more to the left. And if we just to the right, then we have kind of what was cut out before, adding further probability mass. So this one is larger than the other one. Okay, but yeah, maybe not so easy to follow if you just see this now. Okay, and another exercise. So yeah, just to see how it should look like, the task is to change our sample at the top so that our p-values are indeed very low, so that we have a successful test. Okay, so what does not work is to change the deviation, the standard deviation. Yeah, if we make this larger, we get some randomness, but the p-value is still high. So yeah, if we repeat this, we should get a massively different p-value because we added so much more variance. Yeah, but it doesn't work. So what really is important is to change the mean. So let's keep the variance on 1. So now we have the mean. Now we are already at 0, kind of. Just to show you also another important part is really the sample size. So if we are near now, we get still kind of a very small value. But if we have a small sample size, then also our p-value increases. So this is, yeah, because if we have a lot of samples, averaging out is also reducing the variance. So we get results. So just getting more values is massively improving our p-values. Okay, this was this little one. Nice. Okay, and then there comes the more applied stuff. So now a little bit more coding, but not too much, but still, I think very, very mighty concepts. So this is now about do-it-yourself part. And the first thing we want to look at is hypothesis tests. And I just wrote together my little 5-point tutorial on how to do this yourself. The first step I named here is that you yourself can come up with a little test. Yeah, so a statistical test. The key point is that you should be able, given this number, yeah, to differentiate between what would be completely random. Yeah, this is then the H0, completely random data, and your data. So we're going to do this in a second with the t-test. And yeah, there we just want to see whether it's different from 0 or differently phrased. The t-test is often used to compare two samples. So yeah, the question is whether they are separate. So whether the difference of the two is different from 0. Therefore, yeah, this comparison to 0 is kind of another way of phrasing this t-test. And yeah, and if we want to compare the means, then of course, just taking the difference of them would be already a quite good statistic. Yeah, I'm now jumping between the first and the first of these two lists, making the general idea clear with a concrete example. So here, just the difference would be one approach, but we can actually make it simpler for our lives, and we can take the absolute difference, for example, so that we have a clear cut in one direction and don't need to look in two directions. And you can in principle use whatever you want as long as it is kind of, it does what it should, differentiating your specific case, what you want to show from the completely random case. So you could also take the squared difference. That would also work, instead of the absolute. That's all fine. Full flexibility here. Okay, second step is that we should always remember these statistical tests. They have the pitfall that the null hypothesis should be rejected. So we need kind of to do this mind swapping thing that we always need to invert the stuff. So what would this mean in our case of checking whether two different samples have different mean, different average? So we want to show that they are different, and reversing this means that our H0 should represent that they are the same. So the difference is 0. And this is why this fits perfectly into the testing scheme, because this is something quite concise and easy to test. So success, check. We also made sure that we have this inversion correct in our head. Okay, third part I wrote here is think about how your data is distributed if our null hypothesis is true. And what would this be kind of for this example? We, in case we don't know better, we always assume our data is normal distributed. And under our null hypothesis, we know that they have the same distribution. So, and that's what we're going to do. We fit a normal distribution just to all the given data. So because we assume it's the same, we just merge it together. So this is what we're going to do. And fourth and fifth step is kind of now finishing it up. The fourth step is that we do this a couple of times. We sample example data from our H0 and compute our test statistic on this pseudo data, so to say. So this is now a sampling approach. We defined our distribution, and to get our statistics, now we go brute force, so to say. Very naive, simple. And repeat the process again and again. You will see it, and compute our distribution of the test statistic by just getting a lot of samples. So that's why the fifth part is repeat. And now having this sample set, we can look on how likely our target test statistic is. We will see what this means in detail. So concretely we sample and compute our test. And then finally we look at our statistics on our distribution. And for example, we will see that you can do it in many ways. There's a function, Empiric Cumulative Distribution function from the stats base, which is helpful here. So let's do this. I see that Uli is already going. Thank you for joining today. See you next time. So we start with some small data set, just n values. So we have now these two tests where we want to compare whether they have different means. So the one now has here 0 and the other is 2. And and I put a sample size of n here. A standard deviation is 1. And the test statistic, I defined now in Julia function style, in inline function style, just as the absolute difference of the means. So really straightforward stuff. And we can already compute the statistic on our given data. And so next step. So this was step 1 in a sense, but we also constructed additional data in step 0, so to say. Next one is to think about our H0 distribution. So what was the case where everything would be completely random? And here we just fit a normal to the combined data, data 1, data 2 merged together in one big array. So having this distribution, we have a little function now, which we call a couple of times later. So it's quite handy, compact syntax. We use again the inline function syntax and now take random samples from our H0 distribution. And we take the same number of samples to really kind of simulate our case. Okay, and now we repeat our stuff. So we take our test statistic. I can do this kind of separately. So missing a column. So this we do a couple of times in the next line. So we take kind of our first data and our second data, happens to be the very same thing under the hood. And we compute our test statistic on this example data. And we made sure that this is really the same size and everything. So this is a simulation, so to say, from our real data case. We do this a couple of times. So I decided here to take 1,000,000 points. It's a nice little Julia syntax. You can indeed use underscores in these big numbers. And yeah, so now we have a lot of samples. And now there are different ways to use these samples. The one is to use this empiric cumulative distribution function. And yeah, it's just wrapping this. And you can now use this, again, kind of this test statistic here. Use this to see, to inspect kind of the probability mass at this point. So it's cumulative, so everything is summed up. So if I put it just in, you see that, okay, 0.99% lies left to this. Let's actually see whether we can plot this. This would be nice. Not sure, I haven't tested it. Okay, so this is again standard from -5 to 5, so this is always fixed. And we could kind of do it from 0 to 10. Yeah, maybe in 0.1 steps. And yeah, and we see that so this is kind of our distribution, and at the point 1.3, yeah, we have kind of almost all the probability mass already behind it. To translate this into the alpha value, we just take the 1 minus. Yeah, so this would be a very small alpha value, because here we are really interested not in the big confidence interval, but in the edge. And we can write this a bit more concisely, but I wanted to show you kind of this ECDF function, yeah, that this is really kind of the cumulative distribution function. For those of you who know this, this is quite handy to have in a couple of cases. But in case you feel a bit confused now, no problem. You can write it much simpler, and by just using plain functions. And we can directly kind of look at the question which we want to answer. And this is how often actually we find our test statistic or larger test statistics. Yeah, so here actually I use only larger. We could make it smaller equal. And this we can do in Julia very, very simply by using this dot operator. So we compare this one value, yeah, to this whole sample of values. And this dot operator will do the broadcast, so-called, for us, so that every little sample gets compared. So we see, okay, this is higher than our data test statistic, or smaller. And every higher gets a 1, every smaller gets a 0, so to say, a false and a true. And then we just call the mean on it, which will indeed be our estimate for our alpha. So much more concise in this little example. And yeah, it gives the same value, even a bit better. Or looks a bit better. Not sure why this is. Yeah. Okay, so this is kind of the standard approach you can do now with kind of whatever test statistic you want. Yeah, so you just have to think about what would be a nice way, a nice representative value. Yeah, where my feature, what I want to show, in this case, the difference, yeah, pops up quite nicely. And then you need to think about how you want to really model your underlying data. What could be the distribution if everything is random? And yeah, we did this and got now very, very nice results. Of course, I tweaked the arguments a little bit so that these numbers look nice. And there's one special case here I was just pointed out. Yeah. So made it here a question: what would it mean if this value here, this alpha estimator, would be 0. And this happens kind of quite a lot in these settings. And this doesn't mean that you have kind of a 100% win. Yeah, you're totally sure that your statistical test was successful. Now, this doesn't mean it, but this 0 is kind of bound by how many samples you've taken. So going a bit up, we see that we repeated our test statistic. We simulated our distribution, taking 1 million samples. So if we get an alpha 0, this actually means our alpha is 1 divided by 1 million. So yeah, because this is kind of our granularity with which we kind of can see into this distribution. Just nice little thing to know for this approach. And it's super general, super flexible. You can use it kind of wherever you want to make a quick hypothesis test and don't know the precise name of what you want to test. Okay, so little extra exercise. I definitely want to again approach kind of an end at 8 o'clock, but some minutes are. So yeah, so I want to, at least the first point, change the number of observations above and see how our custom hypothesis test performs. And yeah, so let's go up and make it 100 observations instead of 10. And we get our test statistics again. It's now a different value because it's random. And yeah, and we do our sample. It takes more time, but yeah, it's super quick. And I'm going to directly jump to the end and compute our test statistic. And now the case happens, which I just described. Yeah, and this is again kind of the very same behavior, just what we've seen before. If you increase the number of samples, yeah, your statistical tests get much more accurate. So yeah, this is because the law of large numbers, that if you average out a couple of random variables, the lower and the lower the standard deviation gets. Yeah, that's the one of the I think the key result in statistics. So we can also experiment with the distributions a bit more to see how sensitive this is, and usually it works quite well. The reason is because you directly fit it to your data. Yeah, you don't have kind of this. I assume it's super generic. Yeah, but you can make it quite specific. And in our case, we fitted our normal distribution. Yeah, and take this as our H0, and therefore we are very near to our data, and hence we can get actually quite powerful statistics, which are relatively significant. Okay, so last part of today is bootstrapping. This is partly because it's part of StatsKit. So this is part of this meta package, as everything else was. And the other reason is that I myself like this approach very much. When I first learned about it in statistics, I was baffled and stumbled upon it, like, wow, magic. And yeah, it's a very same approach, but with a different target, a different goal in mind. So we again will use sampling, but now to do something different. So what in bootstrapping, we want to find the confidence interval of our estimator. So estimator again is here, like take our standard mean, which we now used a lot of times, many times. And you could ask the question, many don't, but it's in general a good idea to ask yourself how certain you actually are that this, let me say, point estimate is actually correct. So for this, a nice representation would be a confidence interval, so that you can say, with 50% chance, I say it's in this interval. Okay, sounds a bit rough still. So let's say with 95% chance, it's in this larger interval. Yeah, so and then you get a feeling how certain you are. And the difficulty is that we don't know the underlying distribution from where our example data, our sample came. If we would know this, everything is super simple because we can repeat the process or can infer the confidence interval by doing our math, but this is usually not known. We only know the data we've sampled, we have available, and don't know about the rest. So there's another nice framing of this. So we know about our sample, but we don't know about the population, the underlying population of the data, where we sampled from. So the trick now in bootstrapping is that instead of saying, damn it, we have to give up, we say, no, we have our sample. And even if it's not optimal, it's definitely a good guess about what the actual population, the real underlying distribution looks like. And we now pretend that our sample is actually good enough to represent the population. And then we go forward and repeat our process as if we would have seen the whole ground truth. Okay, let me take some water. Okay, let's do it. So I've chosen 1,000 samples here, and I'm generating some normal data again, just for us to feel familiar. And we have our test statistic, which is the mean. Okay, it should be near 0, so that's nice. We would like to know kind of how certain we are. Of course, now we know the ground truth. Yeah, we know that it's a normal distribution, and we could, in principle, get out our confidence interval by doing our math. But let's say we just got this data from the real world, which is normally the case. So we don't know that's from a normal distribution, and usually it isn't. So the key step is now that we just resample from our given data. So this is the step where we kind of pretend our data is the ground truth. It's really as simple as that. So the sample method, I named it briefly beforehand. This is part of the StatsBase package, one of the standard statistical methods which is provided in this StatsBase. And you can input whatever vector you want, and here a number of samples you want to take. And now we have this nice flag of replace equals true. If we wouldn't, so replace means we draw one sample and put the sample back in so that we can redraw it on the next part. And yeah, as we really sample with the same size as we did before with the hypothesis test, it wouldn't make sense to sample kind of without replacement, because then we would just get our original data. And this is now kind of a very simple approach to make a distribution out of your data sample by just sample with replacement. So this is very powerful. Of course, there are other approaches, and I recommend you to look into this package for details and alternatives. But this does very well to represent the idea. And to the best of my knowledge, it's also quite good an approximation. So there's definitely some bias, and it's good to know about the bias. And yeah, so take a look at the package, because these are addressed, but you get the idea. So what we do is then we take our statistic on top of this simulated sample. Yeah, so this is really just the same, but wrapped into the mean value. So this is now one simulated statistical value. And this can be done kind of with any data you want. It's very flexible, again, like we've seen with the hypothesis test. But it's in a sense even a bit more flexible, because it doesn't assume, so we don't fit a normal distribution here, but we just take the data itself, our underlying distribution. Yeah, we just, it's called a non-parametric approach. We just let the data speak, and hence it's even more flexible. Okay, so now we see again the repetition loop here. Yeah, so we get another million of this. And yeah, so the similarity, I hope, is very apparent. So the same approach is super handy, super flexible. And you see kind of computing a million here, yeah, it just takes a couple of seconds. So this is also super fast. And now, for example, we can take the quantile function on top of our sample. You've seen this already. Yeah, okay, maybe this is actually a bit not self-explaining enough. So let's make it even stricter. So we have 90% recover. Yeah. I also replicate the original mean. So now we see that this actually returns something sensible. We have, like a confidence interval between 0 and minus 0.1, which is indeed like, the same in both directions. Yeah, our original one was 0.06. So this gives us an approach. Of course, the big question is this valid? Yeah. So how near are we the ground truth? And it turns out that we are impressively near for such a simple approach. So this actually works impressively nicely. And there are a couple of things you can tweak, of course. And for this, I recommend you to look at the package itself at bootstrap.jl. There are some extra sampling methods and some other estimators. And and for the last minutes, we are actually perfect on time. My last exercise here is to try it with another estimator. So this is also very nice because we are just sampling, and we can hence do whatever computation we would like to. So our estimator can be as complex as it likes. Now the variance is very simple, I admit, but nevertheless, it's more complex than the mean. So variance is very clear. And let's do this. Sorry, I need to adapt, of course, everything to the variance. And I take the same name. No, I leave it. It's just so this is not the mean, but the variance, and we see that this is actually much more stable. Yeah, so the variance itself is very, very stable in this regard. And we again have a 90% confidence interval. I'm myself surprised how stable this is. So nice stuff. And of course, you can experiment with everything also on your own. This notebook is available for you. Question in the chat. Thank you too. Yeah, I plan to share this recording. So going to work on it tomorrow and uploading it tomorrow, and I hope it works out. So otherwise the day after tomorrow. Okay, rounding it up. You've seen a big list of packages at the very front in StatsKit. We've looked into a couple of them. So we've seen kind of some standard tools. First, the missing, which comes from built-in. Then we've seen the categorical array, which is one of the packages mentioned in the StatsKit. So which helps you seamlessly working with categorical data because the levels are always preserved. That's a nice hidden functionality. Okay, then we've looked into kind of the standard packages, statistics, statspace, distributions, and distances. And seeing kind of standard functionality which you would expect in each data science ecosystem. It's there, and it should be already kind of feature complete. In case you miss something, please reach out and file a little GitHub issue. They are happy to add whatever it's missing. And then finally, we looked into hypothesis tests and bootstrapping, where there themselves are a couple of helpful built-in functionalities, but we also seen to use the functionality which we learned today to do it on our own, to do it, kind of bare bones. And this is actually a very powerful way to flexibly work with your data and build some statistics and some confidence intervals. And the last part, which we haven't covered, is that part of this StatsKit is also focused on machine learning. So there's clustering, there's generalized linear models, mixed models, and also multivariate statistics, which is dimension reduction mainly. Check them out. They're just kind of a little bit more an ecosystem on their own, but included here because they are used in many settings. I left them out for today because of timing, and yeah, and they are also nicely looked into on their own. Great. I'll have more time, so thank you all for joining today already. I'm glad we made it on time again. Bye, everyone.